Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to implement Q-learning with an RBF network to solve mountain car. If you don't want to code along, although I highly recommend you do, the relevant file in the course repo is qlearning.py in the subfolder mountain car. At the top, we have a bunch of imports. Most of them should be familiar to you. There's a bunch of stuff from scikit-learn that we mentioned in the last lecture. I pasted the defaults for the SGD regressor class here so that you can see what hyperparameters are being used. You can see that we're using squared error with L2 regularization, a learning rate of 10 to the minus 4, and an inverse scaled learning rate, which means it decreases by 1 over t. Next, we have the feature transformer class, which does all the feature transformations we mentioned in the last lecture. In the constructor, we first gather 10,000 samples from the state space. Next, we standardize the observations so that they have mean 0 and variance 1. Next, we create a feature union of 4 RBF samplers with different variances. The number of components that we pass into the constructor means the number of exemplars. Next, we fit the RBF samplers to the scaled data. Lastly, we make both the scalar and RBF samplers instance variables so that we can use them in the transform function which comes after. Next, we have the model class. Similar to our feature transformer, which was more like a collection of transformers, our model class is a collection of other models, particularly one model for each action. In the constructor, we assign useful instance variables and instantiate our SGD regressors. Notice how we're calling partial fit here with a target 0. As we showed in the last lecture, this allows us to use the optimistic initial values method of exploration. The SGD regressor class also requires us to call partial fit before making any predictions, so even if you didn't want to use optimistic initial values, you would still have to do this anyway. Next, we have the predict method. It transforms the state into a feature vector and makes a prediction of values, one for each action. This is returned as a NumPy array. Notice how we put S into a list before we call transform. This is because by convention, data inputs in scikit-learn must be two-dimensional. A single state is one-dimensional, so this turns it into an n by d matrix where n is 1. Next, we have the update function, which also transforms the input state into a feature vector. Notice how we only call partial fit for the model that corresponds to the action we took. Also notice how we pass in G as a list. This is because scikit-learn expects targets to be one-dimensional objects, whereas G is just a scalar. Finally, we have the sample function, which performs epsilon greedy, which I'm sure you're familiar with by now. Next, we have the play1 function. As usual, we start by going to the start state and initializing done, total reward, and a counter. In each iteration of the loop, we choose our action, take the action, update the model, and increment the counter. We return the total reward so we can plot them later. Next, we have a function that plots the cost to go. As we discussed in the last lecture, this is a plot of the negative of the optimal value function. It's plottable in this case because the state is two-dimensional, which means we can make a three-dimensional plot. Next, we have a function for plotting the running average. This is important because the running average is how you're scored on OpenAI Gym. You also want to make sure your agent's performance is consistent and not just good by chance sometimes. Next, we have the main section. We start by initializing the environment, a model, and a feature transformer. We set gamma to 0.99, but you're encouraged to try different values. Again, I've added a snippet of code so that you can have a copy of the results saved to disk if you pass in monitor as a command line argument. Next, we do a loop through 300 episodes. In the loop, we call play1 and we decrease epsilon geometrically. When we're done, we print the results and make the plots we talked about earlier. Let's run this and see what we get.